Welcome back to another deep dive. Today, we're really digging into what makes our digital world tick. Specifically, we're going to try and break down the key pieces of modern data center networking. And for this journey, we're looking at some really interesting source material. It's practice questions from the JN0-481 exam. Now, that's part of the JNCIS-DC track, the Data Center Specialist Certification. Think of it like a really structured way to get at these core ideas. For us, it's a great window into the fundamental building blocks, from the physical connections right up to how data moves, and even the smart systems managing it all. Understanding this stuff is honestly key to grasping how everything works behind the scenes, like your streaming services, cloud apps, all of it.
Exactly. And that's why this kind of knowledge is so important. It's not just about theory. It's about understanding how you build data centers that are, resilient, efficient, and can actually scale up.
Yeah.
The practice question format, like you said, is pretty neat because it makes you focus on these very specific, critical points for each component. It really helps you get the why behind it all.
Absolutely. So, okay. What are we really unpacking today? We'll start with the foundation, the connectivity layer. People call it the underlay. Then we'll get into the clever ways data travels over that, looking at EVPN VXLAN specifically. And finally, we'll touch on the management side, things like Juniper Apstra, which is all about intent and automation. Okay, let's jump in. Right, let's start at the bottom layer then. The absolute foundation, the underlay in a modern data center network. Now, for anyone maybe less familiar with the newest setups, think about a spine leaf fabric. It's like the data center's nervous system, right? Spines up top, leaves below, super scalable, redundant. So within that spine leaf world, what's the main job, the core function of that underlay network?
Yeah, it's interesting because its main job is pretty straightforward, but absolutely vital. The underlay, its purpose is to provide the basic Layer 3 IP connectivity. It connects all the fabric devices, every spine switch, every leaf switch. It's basically the routing backbone. You just can't have an efficient, high-performance data center without that solid Layer 3 foundation. It's what lets everything talk directly and quickly.
Okay, so it's the bedrock. Make sure devices can find each other at that IP level. Got it. And building on that bedrock, we hear a lot about EVPN VXLAN. That's the overlay technology, right? So when data is moving across this fabric using EVPN VXLAN, how did the devices figure out where specific endpoints like servers or VMs actually are? Which EVPN route type handles advertising that MC and IP address info?
Good question. That discovery piece is crucial for efficiency. It's the EVPN Type 2 routes that do this job. They are specifically designed to advertise the MASI addresses and, importantly, the associated IP addresses of endpoints. This lets devices learn where everything is within the EVPN fabric without resorting to, old-school flooding, which is just not efficient. So dynamic learning is key here for performance and scale.
Type 2 routes, like the network's PIS, finding out who lives where. Okay. Now, flip side. Once data knows the address, how do you keep different customers' traffic separate inside the shared EVPN VXLAN fabric? What does that VXLAN network identifier, the VNI, actually do? What does it represent?
Right. Think of the VNI as like a digital partition. In these big multi-tenant data centers, you absolutely have to keep customer A's traffic isolated from customer B's, even though it's all running on the same physical gear. The VNI is the magic number, really. It uniquely tags each tenant's Layer 2 segment, their broadcast domain. It ensures their data stays completely separate. That's how you get multi-tenancy at scale, sharing resources safely without, compromising security or performance.
Makes total sense. VNI for isolation. Essential for multi-tenancy. Now, managing all this, the underlay, the dynamic overlays manually, it sounds like a complete nightmare as things grow. So automation becomes, not just nice to have, but essential. Which brings us to intent-based networking and tools like Juniper Apstra. What's a core idea behind a blueprint in Apstra? Sounds like more than just a network diagram.
Oh, it's much more than a diagram. Yeah. A blueprint in Apstra is really a declaration of intent. Like, imagine you're not just drawing a map of your city's roads, but you're defining exactly how traffic should flow. Speed limits, one-way streets, everything. The Apstra blueprint is that for your network. Its purpose is to define and then enforce your intended design and all the policies that go with it. The system then uses that blueprint to automatically configure the network. And this is crucial. It continuously checks if the real network matches that intended design.
Wow, okay, so it's not just set and forget. It's a living definition that Apstra constantly monitors against. That's powerful. Now, let's circle back quickly to traffic flow. In these spine leaf setups, why is ECMP equal cost multipath so important? What specific problem does it actually solve?
ECMP is, it's fundamental, both for making things run efficiently and for making them resilient in spine leaf designs. The problem it solves is basically twofold: preventing bottlenecks on some links while others sit idle, and avoiding single points of failure. ECMP lets the network spread traffic across multiple paths that all have the same cost or preference. This is huge because it boosts your overall bandwidth usage and gives you built-in redundancy. If one path fails, traffic just naturally flows over the others. I remember back in the day, a single link issue could cause major headaches. TCMP makes things much more robust.
Right, so better traffic spread, more resilience, optimizes the whole thing. And when you're using something like Apstra to actually deploy these networks, what comes inside an Apstra reference design? Is it just a very basic template, or is there more to it?
No, it's definitely more than just basic. An Apstra reference design, it gives you a really structured, quite comprehensive starting point. It typically includes things like predefined roles for devices. This is a spine, this is a leaf, and the logical layout, the topology of the fabric. It acts as a solid template that ensures you're deploying the fabric consistently, following best practices every single time. And that consistency helps later, too, with upgrades, troubleshooting, all that.
Yeah, sounds like it smooths out the whole life cycle, not just the initial build. Okay, let's dip back into EVPN VXLAN one more time. If you have different VXLAN segments, different VNIs, on the same switch or device, how do they talk to each other? For local routing, what's the role of an IRB interface there?
The IRB interface, integrated routing and bridging. That's the key for local communication. Its job is basically to act as a layer 3 gateway between those different VXLAN segments, but right there on the local device. It's a really important optimization because it means traffic doesn't have to leave the switch, go to some external router, and come back just to talk between segments hosted on the same box. Keeps things fast, reduces latency.
Like a little internal highway interchange for VXLANs on the switch itself. Neat. And, talking about efficiency and keeping things clean, you mentioned Apstra constantly validates. What's the specific feature called that lets Apstra keep checking for differences between the actual network state and what the blueprint intended? And are there common issues like configuration drift that it's good at catching?
Yeah, that's one of Apstra's real killer features: the continuous validation against intent. Apstra is constantly, in near real time, comparing the actual operational state of the network configuration, connectivity, everything against that blueprint you defined. It's looking for any drift or discrepancies. And yes, it's great at catching things like, say, someone manually tweaked a port config outside of Apstra, maybe breaking policy, or if a link goes down unexpectedly, or a device isn't responding correctly, it flags those deviations immediately. It's how it ensures the network stays compliant, reliable, and always matches what you actually designed.
That sounds invaluable for, network hygiene and just preventing problems before they bite you. Okay, let's shift gears slightly. BGP Border Gateway Protocol, we usually think of it for, the big internet routing between different networks. But what role does BGP play inside an EVPN fabric, specifically for the overlay part?
Right, BGP gets a crucial, slightly different role within the EVPN overlay. It's not just routing big IP prefixes between autonomous systems here. In an EVPN fabric, BGP is used as the control plane to advertise that MC and IP reachability information. Remember those Type 2 routes between the VXLAN tunnel endpoints, the VTPs. So the switches acting as VTP use BGP to tell each other which endpoints they know about and how to reach them through the VXLAN tunnels. It's what enables that seamless overlay connectivity, dynamically learning where everything is across the fabric.
So BGP becomes the intelligence, the control plane, specifically for making the EVPN overlay work. Makes sense. All right, final piece then. With all this automation, powerful tools like Apstra, how do you control who can do what? How does Apstra manage user permissions and access?
That comes down to role-based access control, or RBAC. Pretty standard concept, but critical here. In Apstra, RBAC is fundamental for managing exactly who can log in, what parts of the fabric they can see, and what changes they're allowed to make. You define roles like network admin, operator, viewer, and assign permissions. It ensures only authorized people can deploy blueprints, modify configs, or even just view sensitive information. Keeps things secure and operationally sound.
RBAC. Got it. Keeps things locked down. All this precision and automation we discussed, like Apstra constantly checking against intent or ECMP cleverly balancing traffic, it's not just about efficiency, is it? It feels like it's also about taming complexity, making these huge, incredibly complex systems feel somehow simple and just reliable for the people using the applications on top. So the provocative thought maybe is, what does the data center of tomorrow look like when every single aspect is driven by this level of clear intent, constant validation, and automated healing? How invisible could that complexity become? Well, thank you so much for joining us on this deep dive today. We really hope it sparks some interest and maybe encourages you to keep exploring these frankly fascinating topics.